So what we're going to do in part 2 of this video is talk about how we can overcome the limitations of flatMap with Java parallel streams. And there's a very simple workaround. I don't know why they didn't just build this into Java parallel streams flatMap to begin with, but they didn't for whatever reason. And the simple workaround is to use the reduce terminal operation in conjunction with the Stream.concat operation. So here's the same example we saw before, where we're going to have an outer stream that goes from 1 to outer count in parallel, and that will run in parallel. Then instead of using flatMap, this time we're going to use map. And we're going to use map, and map is going to generate an inner stream, which is going to go from 1 to inner count in parallel. And what happens with map, unlike flatMap, is this will return a stream of streams. So you won't end up back with a stream of integers, you'll end up with a stream of integers. And that, of course, is awkward. We don't want things to be a stream of integers. So, but the good news is that will, in fact, run in parallel, as we'll see. And then what we do is we manually flatten this stream of integers into a stream of integer objects by using reduce together with the Stream.concat method. So the Stream.concat method, when used with reduce, will concatenate all the streams together. So it's basically a manual way of doing flatMap that will preserve parallel processing. And then the nice thing here is that our inner stream now runs in parallel, as we'll see when we go and look at the source code and show the output from the results. Because we have to handle the case where the stream may be empty, we have to honor the fact that reduce could very well return it'll return an optional, and the optional could be empty. And if the optional is empty, then we make the stream be empty too. So that's just there kind of for syntactic reasons to indicate that if there's nothing in the outer stream or the inner stream, it's just going to be empty. That's not the case here, but we have to be prepared for it syntactically. And then the final thing we're going to do is we're going to collect the results into a list of integer objects. So now that I've kind of walked through this code at a high level, we're going to switch back over to my IntelliJ project, and we'll take a look at that code, and then we'll run it, and we'll compare the performance, and we'll look and see how it works and demonstrate that it, in fact, runs the inner stream in parallel. So now we're back in my EX35 project in IntelliJ, and this time we're going to take a look at the run test method with the test reduce concat test method. And let's go take a look at that. So part of this is very similar to before. We call the generate outer stream helper method. And just for recap purposes, generate outer stream will create a stream of ints from 1 to the parameter that's passed in, the outer count. It'll then box those up. So we have a stream of integers, indicate we want those things to run in parallel, and then we'll indicate what the outer thread ID was. And since this is all running in parallel, those calls may occur that may be printed out in a different order than the actual operations were invoked. Then what we're going to do is we're going to apply the map intermediate operation. And recall that map, unlike flatMap, does in fact honor parallel processing. So when we look at the inner stream method here, this time this behavior will run in parallel, whereas before it didn't. So again, just a real quick recap of inner stream. We stash away the outer thread ID. We create ourselves an atomic integer that's going to keep track of the count of the number of times that threads are used in the inner stream. We're going to make this hash or this concurrent hash map that maps thread IDs to these atomic integers to keep track of the number of times that particular thread ID occurred. Recall that for the sequential version, the same thread ID got recycled every time for the inner stream. When things run in parallel, though, we're going to see a better distribution across different threads. Then we go ahead and actually implement the inner stream. We go for 1 to inner count. We box those ints to integers. We indicate we want to run in parallel, and this time it's actually going to be honored. And then we call the check inner stream thread IDs helper method. And again, just very quick recap from what we talked about in part 1 of the video. We use the putIfAbsent method on threadMap to go ahead and initialize the thread ID of the thread that we're in to have the atomic integer value of 1 the first time in. And we know it was the first time in because we get back a null as the result of putIfAbsent. If we don't get back a null, that indicates that we've looked something up that was already there. There was already an atomic integer that was stored under that thread ID in the in the concurrent hash map, in which case we just increment by 1. That would indicate there was sharing of a thread within this particular inner stream. And then once we've gotten to the max iterations, we print out the contents of the thread map. Now, what we're going to expect to see when we run this program here is that we'll have different threads running in the inner stream. And to kind of wrap things up, we get back this stream of streams of integer objects. We then do the reduce call to reduce that to a single result. And we use Stream.concat as a method reference to basically concatenate each of the streams into a single stream. So we end up with a stream of integer objects as opposed to a stream of integer objects, which is precisely what flatMap is attempting to do, except that flatMap doesn't honor concurrency and it runs everything sequentially. And then we collect the results into a list and print the results. So let's go ahead now and run the program, and you can see some interesting results. So if you remember before, when we had run this, we had an outer thread IDs, which were all these different IDs, but all the inner thread IDs were always the same for every element that was being processed in the inner stream. When we come down here in contrast and look at what we've got for the test reduce concat, instead what we have here is the outer thread IDs, which are, again, whatever they are, they're all different, in fact. And then if you take a look at the inner thread IDs, you can see that we actually have different thread IDs that are being used there. And in fact, in some cases, quite different thread IDs. So if you take a look, for example, thread ID 20 is the one that will run for the iteration count of 5. And you can see if you look at the inner stream, one of the things is done in thread 21, another one is done in thread 22. 2 of the operations are processed in thread 24, and another one is processed in thread 26. And so that's demonstrating quite nicely and intuitively that we have multiple threads that are running in the inner thread stream, or the inner stream. There's inner threads with plural, the emphasis on the plural, in the inner stream. And that is distinct from what we saw with flatMap, which only had 1 thread running in an inner stream. And all the processing was taking place sequentially in that one and only thread. And then perhaps the most interesting result here, which really underscores why the reduce concat model is preferred, is if you take a look at the running time, you can see that the time taken to do the processing for test reduce concat was 4 milliseconds, whereas the time to process the flatMap was basically 60 milliseconds. So it's a substantial speed up, and on my 8-core processor. And then keep in mind, it's 8 hyper-threaded cores. So it's basically, I guess 16 processors. So it's basically scaling up almost linearly with the hyper-threaded cores. So that's a great result and demonstrates why the combination of reduce concat can often be used in lieu of the lame, limited flatMap when it comes to running things in parallel streams.